So this is problem number 31, a ladder problem. So just to emphasize here, our free body diagram, this is the force of friction actually from the ground, and this is the force from the wall. And those are our two x forces. So this is a static equilibrium, means everything adds up to 0. So then in the x direction, then we can have those two forces add up to 0, which means they equal each other. So the net force, So the net force in the x direction is this force of friction to the right minus the force of the wall, which is a normal force to the left. Now what about the y direction? Let's look at our y forces. We've got the weight of the ladder itself, we've got the weight of the woman painter here. Those are down, so it's up. It's just this right here, which is really just the force normal from the ground up. And those are all my y forces, and they all have to add up to 0. So I'm just going to rename these a little bit. I'm going to call the weight of the ladder mg1, weight of the painter mg2. And so force normal up minus those two weights should all add up to 0. And that's nice because that means I can immediately solve for Fn over here because they equal a combined weight of both of these things. So let's do that. So I'll move this over here. So the force normal will equal these two, and put the mass of 12 kilograms in here times 9.8, mass of 60 here times 9.8. So the force normal up from the floor is 705.6 newtons. All right. Let's go back to Fx and let's solve him. So the force of friction must equal the force of the wall. And remember that Ff equals Fn mu, and now we know Fn. So replace Fn mu now, and so we can say, we can plug in Fn right there. Okay. So now we need to find the force of this wall here to determine mu, which is what the problem wants to know. But we're out of equations here, which means we have to turn to torque, making the net torque equal 0. All right, so to have any torque at all, you got to pick an axis of rotation. And so I would pick this point right here, because that means this force of friction this way and this force normal up from the ground both have 0 torque because they're acting right at the axis of rotation. Therefore, they have no lever arm, therefore they have no torque. So about this axis, you just need to imagine the ladder can rotate this way or this way. These are counterclockwise torques, and these are clockwise torques. So the forces that are generating torque are force of the wall this way, counterclockwise, minus these two weights clockwise. So this torque must be equal and opposite to that torque to keep the whole thing in static equilibrium. Now the hard part is, what are the lever arms? Here's the force, but these are not perpendicular. So where are the perpendicular lever arms? Okay, so if I drop this down like that, if you can imagine that, then this distance from here to there is the lever arm for mg, m1g, because here is where they meet in a right here is where the perpendicular distance between the force and the axis of rotation. That's the definition of lever arm. Since this whole distance is 3 meters, and we know this is at the midpoint of the ladder, then this must be 1.5 meters. So here would be our torque equation. This is the positive counterclockwise torque, and these are the two negative clockwise torques. That all has to add up to 0. But these are torques. So to make them into forces, we need to take the force of each one times each one's respective lever arm. So let's do that. So as I just said a second ago, the lever arm for M1G is going to be 1.5. So this value would be 1.5 for his lever arm. His lever arm, they just simply tell us, or her lever arm, would be this distance here, which in the problem they say is 2.1 meters. So 2.1 meters would go there. Now for the force of the wall, here's the wall. If I extend this out, let me just sort of draw this a little bit. If I extend this out this way, you can see, all right, if this is the axis of rotation, this is where they meet in a perpendicular right angle, right there, which means this distance right here is the lever arm for the force of the wall. And we know that that is 4 meters, and so 4 meters would go into the lever arm there. Now if you look at this equation, the only thing we don't know now is Fw. So if you plug in all these values, we solve for Fw. If we solve for Fw, we know this, and knowing this, we can now solve for mu. And if you plug all that in, you should get an answer of 0.5. It's a little bit over 0.49. I think you round in as 0.5.